Okay, I'm officially recording, and if you remember at the end of last lecture, we have a problem. I just draw a figure, and now let's just solve this problem. It would be a problem something like this. Have a shaft like that, and then another shaft here. See, and then it's connected to fixed conditions here. Just under the. So let's see. I have a torque here is the 5 kilonewton meter, and the torque here 10 kilonewton meter, and the torque here 7.5. Let's see, this is point A, point B, point C, and point D, right? At least something like that. So the diameter of this one is 7 centimeter, and the diameter of this one is 10 centimeter. So we ask to find the maximum shear stress in the shaft. That's right. So, okay, let's just the same as statics, since we have a three torque here, just find, okay, the formula is this one, right? So first, just review the formula, maybe you forgot. This is the formula to find the shear stress, right? So R and J could be the material parameters. R is radius, J moment of inertia, and T is a torque. We should find the torque in each section. So here we have a torque, the external torque here, and until this point C, there is nothing, so we can make a section here, draw the free body diagram, for example. And then we have this torque here from point C to point B, then we can make another section here to find the internal torque, and then we have another torque here. So it's the same as the bar. In the bar, we have axial force, here we have torque, right? So let's see, for example, let's start from segment CD, right? So we can draw something like that. So this is the 5 kilonewton meter. Let's just this direction. This lets me denote TCD, right? So let's say summation of the torque or summation of the moment, and it is 0, something like that. So you can set the TCD plus 5 equals 0, and then TCD would be negative 5 kilonewton meter, right? This is for segment CD. And then for segment CB, let's find all the torques, and then we can talk about the shears. That's right, CB. So we have something like that. And then we have maybe another. So this is 5 kilonewton meter, this torque. We have one torque here. It's the other direction, right? 10 kilonewton meter. And then let's denote this one, for example, TBC, TCB, something like that. If we put the summation of the torque here equals 0, let's see, it would be TBC. The 10, look at this 10 is in the opposite direction, right? Let's write -10 and +5.
Is there a reason we choose down for TBC instead of up?
It's just an assumption. It doesn't matter. But if you use this assumption, you should use the same assumptions for all the segments, right?
Like the right-hand rule.
The CD, right? For example, if you make a segment for, if you make a section CD, BC, AB, so you should make the consistent assumptions for all of them, right?
Got it. Thank you, Professor.
Yeah. Let's look like the shear diagram, moment diagram. No, in the statics, we use the same assumptions for. So
is this like the last chapter where we include the torsion force from all of them if we keep going further to the left? Like for the next one, we'll include the 5, 10, and then
yeah,
the AB. Okay.
Yeah, I wanna this one. And then because you have one more forces, right? Then so this is this one. It goes there. And then let's see for AB. Let's maybe something like this, right? So now let's put all the torques. This is 5 kilonewton meter. Then we have this torque 10 kilonewton meter. Also we have 7.5 kilonewton meter, right? And then let's just, this torque would be TAB, right? So summation of the torque because of the equilibrium is 0. Let's TAB 7.5, negative or positive?
Negative.
Negative, then negative 5, the same as our assumption. 17.5 minus 5, TAB would be 12.5 kilonewton. That's right. So let's now review the equation again. So this problem asks us to find the maximum shear stress tau. TRJ. Okay. Now it's good. We find T, and the maximum shear stress in this figure. Let me zoom out. Okay, just I will zoom in, but let's just show all. So T, you know, look at for example, CD. The CD, the torque is 5. The TAB is 12.5. TBC is 5, right? Okay, first BC and AB. 12.5 is greater than 5. And also in segment AB and BC, look at here. AB and BC, the same radius, right? The radius R is the same. And if you find the moment of polar moment of the inertia, J also would be the same, right? Because J, what is J? The formula for the J is the pi d to the 432, right? So, which means for AB and BC, J would be the same, R would be the same. Therefore, for sure in segment AB, we have more, the shear stress is greater than TBC because TAB greater than TBC, right? Because radius would be the same, J would be the same, and since TAB greater than the TBC, the shear stress in segment AB is greater than BC. But the problem for CD, in CD, okay, T, the torque is less than TAB, but J also less than, and J is the denominator. When we decrease the denominator, maybe the shear stress increase, right? So therefore, for TAB and TCD, we are not able to just look at this number and then say, okay, the shear stress would be max at this for this one. We should find R and J because here T is greater than TCD, TAB, and numerator increase, but in segment AB, the polar moment of inertia greater, and for CD is less than, so then TCD is less than, which means when we decrease the denominator, the ties increase, right? So when we decrease, yeah. So for AB and CD, for each one, let's just separately find the shear stress and then just compare which one is greater than. We can conclude, okay, at which sections we have a maximum shear stress, right? So now let's write from AB first. For BC, we don't need to calculate because BC is clear. AB is greater than BC and R and J is same. So let's just, the two sections would be AB and CD, right? So TAB, what is TAB is 12.5, right? What is R? RAB?
5.
It's 5, and I divided 5 to 100 because the T is based on kilonewton meter, but the R is based on centimeter. Just I divided by 100. This 100 means centimeter to meter, right? This 1 over. J, J is pi D, and let's again divide it by 100 to the 4 divided by 32. So the answer would be, if we solve this problem, would be kilonewton per meter, or we can divide it by 1063.7 megapascal, right? It's kilopascal just divided by 1000 with megapascal. And for segment CD, tau CD would be TRJ CD. T would be 5. What is R here?
Isn't it the same thing? Oh, CD.
Yeah, for CD, what is R?
3.5.
3.5, right? Yeah, the diameter is 7, the R would be 3.5, right?
Does the fact that the torque for CD is negative mean anything?
That's because of the equilibrium. The only things is because of equilibrium, but we don't need to, for the shear stress, we don't need to include the sign. The only thing, since we assume this direction is positive, which means in the opposite direction to sustain about this phi, right? Does it make sense?
Yeah, thank you.
Mm-hmm. So in this structure, what's the maximum shear stress? Tau max would be?
63.7.
No, it doesn't ask us about to find torque or no, just the maximum shear stress, maximum shear. Just compare these two, just 74.2, right? Yeah, 74. Those things you are asking about to find the minimum. Yeah, I want to solve some problem again like that. If we want to find the maximum torque and then we have a allowable stress for two different material, we should compare those things. Yeah, but here it's just we want to find the maximum shear stress, right? The maximum, which means it's very similar to statics, right? So just the maximum shear stress. So it doesn't care about the allowable, or it doesn't say anything about that. J for CD power 2. Oh yeah, I did wrong. Thank you. It would be power 4, right? So it could be tau max would be 74.2 megapascal. Maximum shear stress in these structures, right? It happened here in this segment, right? So can you please correct? J is the J, as we discussed last lecture, is the polar moment of the inertia. Yeah, J is the polar moment of inertia. Yeah, we derived this formula in last lecture. I think that was J is this formula, right? The original formula. And we need to discuss from this formula to this formula, we should wait for chapter 4 to cover about the moment of inertia, and the polar moment of the inertia is some case of that, right? But in last lecture we derived this one, this formula. We derived the polar moment of inertia, right? It means shows the position of the force in any point. Yeah, it shows the position of any point regarding to the axis, right? So we should discuss about it. Does it make sense to you? Okay. So this formula is tau TRJ is the first things we discuss and we solved. Yeah, that was the second problem we solved. So here, and so that's everything we need. That's a relation between stress and the torque, shear stress and the torque. But if you remember in last lecture, we said another important parameter in the torque, in the torsion chapter is the angle of twist, right? We talk about, we show the angle of the twist phi on the section, and we said it's something like it plays the role of, for example, it's similar the role of the elongation on the axial bar, right? In the axial bar, we have a normal stress, and then we have elongation, but in the shaft, we have a torque, and then the deformation should be shown based on angle of twist, right? So let me derive again, for example, a figure. So the angle of twist, so it would be, for example, if you have a torque here, yeah, if for example you have something there, right, and then it's something. Last lecture, yeah, we have something like that. And then we said, okay, here in this figure, we said, okay, let me show you the other color. If in this section we have maybe this point is P, and then this point after applying the torque is P prime. And then we said this angle here, this angle is phi, and said this is angle of twist, right? This is angle of twist. So in the section, so like that, right? If you look at here, we have something like this, right? The cross section. If this is point P, if go to point P prime and this. So, and then this angle shows, so for any material, for any problem, sometimes it's okay. So, you know, in the bar, if you remember for the bar and the actual force, under the actual forces, right? You set the allowable or maximum elongation, something like maybe 2 inch, right? Something like that, or 1 inch. The same for the torsion case, for the shaft, we don't have elongation, but we said, okay, the allowable angle, this angle would be, for example, 2 radians or 1 radian, something like that, right? So these things play something that's similar, the role of the deformation, right? Something like that. And now the question is, how can we find this value, right? So now let's we should review the formula from the last lecture. So in the formula, we had something like that. So we have a stress-strain relationship, right? So we talked about this formula before, and also tau. Okay, tau we said TR over J or T rho over J, right? We said this formula, and one more formula we discussed last lecture about the formula for strain, right? The gamma would be rho phi divided by L, right? So we discussed about all this formula last lecture, and now let's just substitute, just instead of tau, put this one, instead of gamma, put this. Let's see. What is tau? Tau is T rho over J G. What is gamma? Rho phi over O, right? So the phi could be canceled both, and then angle of the twist, sorry, rho cancel, angle of the twist would be TO GJ. Now it's very interesting, right?
What does the G stand for, Professor?
G shear modulus.
Okay.
Right.
So we're going to be given that usually?
Yeah, it's a material property.
Okay.
Elasticity of modulus, shear modulus, these are material properties are given, right? So it's very interesting. Let me recall something. Do you remember in the chapter for axial force, we have delta. This is a scratch work you didn't need to. PL over AE, right? Do you remember this formula?
Yeah.
Okay, now compare. For axial bar, we have force P. For the shaft, we have torque T. The length of the bar, the length of the shaft. E, elasticity of modulus. G, shear modulus. Right, let me rewrite this one as EA, maybe. A, cross-section area, the properties of the cross-section. J, again, moment of inertia, again, that's the properties of the sections, right? Because A, for example, A for the circle is pi r squared. J for the shaft or circle is pi r squared divided pi r to the 4 divided by 2, which means A and J, both of them depends to the just cross sections, right? Radius or diameter or something like that. You know, we can map these two chapters together, right? It's very interesting. What does the L? L represent the length of each segment. For example, if if you have maybe a segment, something like that, right under the torque, right? This L is this, right? So for this case, for example, here could be L, or if you find an angle of twist here, this could be L, something like that, right? This is the length of the shaft. Does it make sense to you? Okay, so you know, this is chapter 2. This is chapter 3. So you can map, so you know, is elongation is angle of twist. These two formula is very similar to each other, right? So then, for example, the same as the elongation. So for example, let's assume, again, we have maybe, let's assume we have this shaft, right? And if you remember, and then again, if just I'm drawing the raw figure again, if you have this, for example, C is B is A is under this torque, right? So so just keep this one here in the left hand side, and then just back to chapter 2. To chapter 2, for example, we have bar, something like that, right? Just let's add bar, for example, P, right? This is chapter 2. So let's just A, B, C. So, you know, remember in the delta, we said, okay, we said delta AB plus delta BC, right? That would be the total delta here, the total delta, right? Now, it's very similar here. Instead of delta, we said the angle of the twist, at the total angle of the twist would be angle of twist for AB plus angle of twist for BC, right? So which means here in these sections, if you look at these sections, so you have this angle of twist, right? Here, if you have this phi, then to find this phi, so again, the same as this is chapter 2, right? The same as chapter 2, we should make a segment here, then find the T, find the G and J, L and G given, find the J, and then maybe go to this segment and find the angle of twist. So which means here we have angle of twist A respect to B, just this segment, and for this segment, B respect to C, and then this is fixed, right? Then we can add to each other, right? So this is current chapter. This is, so you know, if you understand well the chapter 2, now this is very, very similar, but with different, just with different parameter and symbol, right? So, and in the previous, so the previous example I solved you know, because of that is I pick that example because I make a section and find T. And now for this type of problem, I want to again solve another problem. And then first of all, we need to make a segment and then find the T and then find the J for each segment and then check if G is the same or different and then find the phi for each one and then find total phi. And this total phi is maybe is the role of the deformations, the total deformation of the shaft, right? And then if the allowable deformation is given, we can compare with that, we set is okay or not. And we want to solve some other problems. For example, if allowable phi is given, how can we find the diameter or something, which means design the shaft, something like that, right? So by now, but now I want to just, we have a new formula, this one. Okay, does it make sense, this formula to you? No?
Yes.
Okay. Now is a good time to solve the problem. I'm gonna solve the problem. Okay, let's see. I have I wanna draw, I try to draw nicely. This is a shaft here. Then shaft, and then let's see a bigger shaft here. There maybe. My drawing is not good, but let's see this cross section. Okay, and then this shaft, and here we have just a fixed support, just as a support, right? So hopefully you can imagine. So we have this shaft, and then we have this, and from this section we have hollow sections. All right, let's see. Apply some torque here. 250 Newton meter, and here we have 2000 Newton meter. Okay, that's these two. Right. This diameter is 30 millimeter. The diameter of this shaft is 60 millimeter. And the inner diameter of this part would be 44 millimeter, right? So guys, before writing about the dimension, what if we want to solve this one, how many segments do we need? What do you think? Just give me numbers. 1, 2, 3, 4, 5. How many?
Is it 3 or 4?
Don't say or just say 1. 3, right?
3.
3.
Yeah, I got lots of answer 3 in the chat. Okay, 3 from, so here we have one segment, then from here by the beginning of this one, and after that the section change, right? So we have a 3 segment.
Professor,
Yes.
did I say 41 or 44 inside the
44. So it's,
So we'll just subtract that from the area, right?
yeah. It's 44, right? Yeah, I should. Actually, we don't need area. We need a polar moment of inertia, right? Area is good for the actual, but we wanna have a torque here. Guys, does it make sense, the figure to you?
yeah.
Okay. So, okay, let's see. G for all the material, for all the segments is would be constant. 77 gigapascal. Right? So, okay, we want to find just phi total, right? And let's just denote this point is A, this point is B, this point is C, and the last point is D, right? A, B, B, C, C, D. Find angle of twist, right? So phi would be phi AB plus phi BC plus phi would be phi AB, be related to phi CD, right? We'll find angle of twist, right? So let's start to find, okay, what is formula for each segment? So for each segment, we should find TL over GJ, right? But let's just now back to statics, just make the segment and find the T.
Summation of the T.
Right, exactly. So let's start. The first thing in my note, I have the segment CD. Let's make use. Okay, we need to make a section somewhere here. Make a section somewhere here and make a section. Let's first from CD. Let's see for CD. So let's just draw a schematic figure. And then we have this figure. Right. Just check my, and we have a segment here. Let's just assume this is TCD. So we have 250 here, right? And 2000 here, right? Summation of the torque equals 0. Let's TCD. Just make sure about the sign, right? What is the unit?
Newton meters.
Newton meters, right? This is segment CD. Let's go for segment BC.
Professor, did we not add TBC and TAB to TCD?
TBC, TCD, TAB, all of them are internal torque. Once we make a section, they appear, right?
Okay. Thanks.
Yeah, these are the external. It looks like, for example, being under the external forces, then we make a section, find the internal forces. But now we said maybe instead of forces, an internal torque, right? 250, and this is 2000. In this section also is the same as this one. TBC. Summation of torque is 0. Would be TBC minus 2000 minus 250 is 0. TBC would be 250 Newton meters, right?
Professor, the reason why we did an extra segment like the C is because there's like the hollow portion.
Exactly, because of this one, this hollow effect on the J, right? If we check this formula, the problem of this hollow is effect on this parameter. Then I make an extra segment, right?
Okay, that makes sense. Every time we have like a hollow or like a force or moment going around, then we do a segment.
Exactly. If this cross section change, if the new force coming, if the material change, right? We should.
Okay, thank you.
Just guys, try to draw nicely. This summation T0 TAB minus 250 0 and okay. Does it make sense to you?
Yeah.
Okay. Okay. Let's see. Let's go to the now. This is T, L is given, G is given. Let's find the J also. Let's go to the each section. Let's start from AB. Cross section look like this, right? What is the radius is 15, right? J would be PD to the 4, 32, or P to the R to the over 2, right? In previous problems, I used this formula. Let's, for this problem, it's something different. Let's just solve based on R, right? But it doesn't matter. You can use 30, but let's just use based on R. It's something different. Every problem by problem, 15 divided. I divided by 1000 to change the millimeter to meter, right? So guys, now please give me what is the unit.
Meter to 4.
Meter to 4, right? For BC, we have this. It could be this radius, could be 30 millimeter, right?
Professor, how come you use oh, because it's 60. Never mind.
And the segment CD, we have hollow sections, right? What's that? Does it make sense to you? Divided by 4. Does it make sense to you guys?
Yes.
Okay, these are the 3 J's. Now, let's construct the formula. Let's start from CD. Can you help me to write this one? What is T?
$2,250.
Yeah, 2250. What is L? What is L?
6 meters.
Yeah, 0.6. And J, we find J here, right? 0.9. Right? I'm not very serious to show but this is radian, right? But if you don't show the radian, that's fine.
Hey, Professor,
Mhm.
why is J m to the 4 again? Units wise?
J, because J is pi r to the 4, right? Then r, the unit of r is meter, right? Then this unit of power to 4, right?
Yeah, but like conceptually wise, like wouldn't it be like volume times something?
No. Conceptually, again, I need to cover something for moment of inertia first. Then we will understand about that.
Oh, okay.
Yeah. No. It's totally different from area. Don't confuse about that.
Okay, thank you.
Yeah, I wanna show you something on beginning of the chapter 4 actually, because the book assumes the students know about this, but some of you may be learning the statics, some not. But in the beginning of the chapter 4, I said moment of the inertia, and then J, we should then improve the moment of inertia to polar moment, and then I will understand. But it's totally, but in general, it's something about if you have a sections, right? In generally, as it shows, it shows the positions of any node to the axis X or axis Y. For polar will be combination. So then we gotta solve the problems about focus on some portion and then talk about the position of each point and then take the integral. Then you will understand about that. But right now, just follow the formula. But maybe in a few lectures, I just talk about moment of inertia, right? Does it make sense?
Yeah, that works.
Right. Yeah. What is BC? What is the force in BC?
2,250.2.
Mm-hmm. What L? Let's check 0.2. Just JBC 1 point. If you remember in chapter 2, I said the elongation is a very small value, numbers. For the same, for the angle of 3 is also, it should be very small value, something like this, right? If you reach the large value, something maybe 1, 2, 5, and so for sure you have some error or mistake during the calculation, right? What is T for AB, segment AB?
250.
250. How about L?
0.4.
0.4. Do you know why I multiply G to 10 to the 9? Do you remember?
To convert to Newton over meter squared.
Yeah, to convert to Pascal, right? Because now it's based on gigapascal, right? Okay, lots of calculation, right? So we find in each segment phi A about B, B rather C, C rather D, and now angle of the twist with the summation of the angle of twist for each segment. BC plus CB. this is okay if you are asked to show the results based on, this is okay. But if you're asked to show the results based on degree, there's one more thing. I will not ask you about that. Let's just, that's so. Does it make sense to you guys?
Yes.
Okay, that's very, very important problems. So, okay, let's solve another type of problem. Okay, now, okay, we said, so we already now share stress based on the torque TR over J. So maybe tau allowable is given, and in the last lecture, right? Tau allowable was given, and then you find the torque. And now let's just solve a similar problem. What happened also, not only tau allowable, maybe angle, the allowable angle also given. Maybe something is already designed, want to design something and said, okay, the maximum angle in the shaft would be this value, maybe something like that, right? 1 degree, 2 degree. And then what number of the torque, what's the maximum torque we need to apply on that, right? Something like this, right? So let's assume something like this. Let's just shaft. Yeah, this class is very important. We need to solve many problems to understand the concept of this class. Actually, this type of problem is like complex analysis. Next lecture, we want to talk something about design. Okay, this is my drawing is not good, but this is a support. So, okay, let's see. This is brass. This is steel. But we have a torque here, not in this end, right? But you know, this is the angle of twist here, but we have a torque here. The torque applied there, right? Four feet, 6 feet. Both material has the same diameter, 4 inch. Okay. Let's see. Let's write the input data, given data, sigma tau y would be the 36 KSI. There is something in the chat. G of the shear modulus. Right, and then for steel, yields and G of steel. PSI. Right. Assume factor of safety for both material. Let's assume 2. And phi max or phi allowable. Anything we wanna maybe allowable or max would be just 0.15. That's great, right? Find now find the maximum torque T, right? Let's see. Let's sign my notice F. This is E. This point is D. This point is B. I have these notations. So, okay. How many? So, let's see. One thing, yeah, we solved several problems right now. So in this segment, actually, if you make a section, there is no force, right? Do you agree with me here? There is no torque, right?
Yeah.
So which means if you make a section, there is nothing here. So if you put the torque, that torque is 0, right? So then phi BD would be 0 here, right? There is no torque, right? So that I'm talking first about the second. And then we have make a, we should find one section here and one section here, right? It's because this phi BD is 0, right? There is nothing. So maybe these two sections. And then in this problem, you don't need to make each one separately. It's very simple. If you make a section here, then the torque would be equal to this torque, right? If you make a section here, there is no torque between here, this point E after E, right? Which means because of the equilibrium, the internal torque and this section for whole any point after D would be the same, right? Do you agree with me? Right? So what does that mean? Which means phi, let's write formula for phi, would be phi EF plus phi DE plus phi BD, right? So this case is 0, right? Because if you make a section here, there is no torque. The summation of the T equals 0, then T is 0, right? It doesn't affect on the answer. So for these two, if you make a section at any point, so the equilibrium, the torque will equal this torque. The torque here equal. So the both forces will be the same. The same as the previous problem, and two sections we have 2,250, right? The result will be the same because there is no torque between D by the end. We make a sections, right? Will be the same. So then, okay, we can directly write a formula, right? Phi, maximum phi is given 0.50, right? Phi EF we can write like that, TL GJEF plus TL GJ for DE, right? Now let's just substitute and then find the T, right? And now help me for substitution. T, we want to find T. What is L? L of the L of EF.
6 times 12.
Yeah, 6 feet. Let's just multiply 12 based on inch. This 12 would be feet to inch, right? G, what is G?
5.6.
5.6 times 10 to the 6, right? And J, let me find the J, because J for both material would be the same because we have the same diameter, right? Let's find the J and then we can substitute. J. Let's find the J. J would be the pi d to the 4 divided by 32. And the answer would be 8 pi, right? That's a J. Now it's easy, just substitute J here. Just 8 pi, right? Plus the segment DE. T, what is L?
4 times 12.
4 times 12. What is G?
11.
11 times 10 to the
Yeah, because we are in this section of steel. Okay. So use the algebra, just one equation, find the T. That's the maximum phi allowable. Then the T would be 219. Can you give me the unit?
Inch pounds, right?
Pound, inch, and yeah, I think the results would be, because this is the PSI, right? These are the PSI. Yeah, the answer I have, this one, pound, inch, and also you can write based on kilopounds. Yeah. So guys, if the problem just give us a phi allowable, that's good. We can stop this problem here right now. But the problem also give us some information about shear stress, tau, right? So let's find also torque. So this, find also based on this formula. Because we have another formula, and now tau allowable also is given, right? So tau allowable is given. J for steel and brass would be the same because the same radius, and R is the same. Just let's find the Tn. And now let me ask a question: which tau should we put here? Tau for steel or brass?
Would it be the bigger one?
Now that's the things. We should use a smaller one, right? Because, okay, let's look at here. Here we have 36, we have 21.6, right? If we pick 36 and we find the torque, right? And then if we, okay, let me write just as a review something like last lectures, right? We have we solve problem last lecture. Right? If we use this tau and we find t, then if we put t for the brass and then find the tau, then tau would be greater than 21.6, and then that's not good. Therefore, for this formula, we should look at this number and this number, pick the smaller one, right? If we pick a smaller one, and then once we find the t, and then this, if we substitute t for the still, and the new tau would be less than 36, right? You can check for both, is a good practice, but in reality, if you remember from the last lecture, we said in this case, if we find the t based on this value, if we find based on that value, and then the smaller one is the results, right? Do you remember? Then I checked the results, and then one of them that was not acceptable. It would be the same. So now for this case, steel and brass both has the same radius, same polar moment of inertia. Let's just pick this one, right? At the end, then we can also check if you want, I show you. But let's add a second criteria right now. But 21.6 factor of the safety is given, right? Is 2, right? Because we want to find tau, because we want to use tau allowable, right? This is factor of safety. T, what is R? J is 8 pi. What is R?
2.
2, yeah, radius of the shape. And using this formula, T is the value for T would be 135.7 kips inch. And now again, compare these two. Which one would be the answer?
The smaller one?
Minimum. If we pick this one and put it here, then tau allowable would be greater than tau. The tau would be greater than tau allowable, right? So that's the answer, right? So we have some minutes if you have question about this problem or something is wrong, or we can discuss for 5 minutes. And next lecture, we wanna show you a problem how to measure how to find the diameter as a design problem. Does it make sense to you?
Sir.
Yes. Yeah. Okay. If you have question, you can ask me. Thank you. Or feel free if you want to leave the session.
Did you say the factor of safety was the 21.6 or 21.6 divided by 2?
Yeah, factor of safety is 2.
Oh, it's 2. Okay.
Yeah, sigma allowable is tau y divided by 2, right?
Yeah.
So we always gotta find a tau through phi, and then if we're given a tau of the material, then we find a different torque with that one.
Yeah, if the tau y, so you are saying always what? Always find t?
Yes. So in this case, we found 2 different torques.
Yeah.
Right. So
Yeah.
how do you know when you're supposed to only look for 1 versus 2 torques in one problem?
Yeah. If only phi is given and only tau is given, just we should find one t. But if both criteria are given, the allowable stress is given and allowable angle is given, then we should find the two, because we have two formula available, right? One formula for phi is TL over GJ, and one formula for stress TR over J. And based on each one, we can find the individual T, right? And then we should pick the smaller. But if the same as the problem in last lecture, only the criteria for stress is given, tau y, then okay, the only we need only to use this formula, right?
Okay, yeah, that makes sense.
Yeah.
Thank you.
Just read the statement carefully here. The given data here, tau y is given, phi allowable is given. So since we have these two cases, therefore we should use the two formula. Tau TRJ, this is one criteria. The other one, this one, TL over GJ. We should check both of them. But if it said, okay, find the torque if sigma allowable this, and it doesn't say anything about tau, then just only use this formula. Right?
Yeah, that makes sense.
Thank you.
Can you go back down, Professor?
Okay. Here?
Okay, thank you. I was just double checking my answer.